Welcome back to this new video. In this new video, we will look deeper into the Chinese remainder theorem. We will define it, we will see how it works, we will have the proof, and then we will apply it on different numbers. The Chinese remainder theorem will be very useful in the use in computer science and in number theory. The first thing that we have to say is that we are looking here at solving a system of linear congruences. Now, we looked at solving a linear congruence in the previous video, but now we have more congruences that we have to comply with. And in fact, the method that we are going to develop is in fact a method that are at the basis of multiplication or addition of large integers. So basically, the solving of the system of congruences will provide the methodology how to do mathematics with large integers. Now, let's have a look at a problem that has been described by the Chinese mathematician Sun Tzu, which said that there are certain things whose number is unknown. When divided by 3, the remainder is 2. When divided by 5, the remainder is 3. And divided by 7, the remainder is 2. What will be the number of things? So basically, this is an expression which is in fact related to modular mathematics and to congruences. Basically, the first element says divided by 3, the remainder is 2. So x is congruent to modulus 3. The other one, when divided by 5, the remainder is 3. So x is congruent with 3 modulus 5. And divided by 7, the remainder is 2. So basically, we say that x is congruent to modulus 7. And this is the basis of the Chinese remainder theorem. So basically, we have to find the theorem. How can we find the value of x? The proof of the Chinese remainder theorem will be done in the following videos, but first we have to describe the remainder theorem as it is known. Now, the Chinese remainder theorem states that when the moduli of a system of linear congruences are pairwise relatively prime, there is a unique solution to the system modulo the product of the moduli. So basically, we have different moduli, m1 up to n. They are pairwise relatively prime, so that means that their GCDs are in fact equal to 1. And they're also, we have the positive integers that 1 and a1, a2, and an. When we have those greater than 1, so the m's are greater than 1, and we have the coefficients a1 up to an, then we can say that the system of congruences x is congruent with a1 modulus n1, x is congruent with a2 modulus n2, up to x is congruent with an modulus nn, that we can say that this has a unique solution modulo m, big M, capital M, which is the product of all the moduli, and it means that there is a solution between 0 and m, so x is larger or equal than 0, but smaller than m, and all the other solutions are congruent modulo m to this solution. So basically, we have one solution, but we have more solutions, but they're all congruent modulo m to this solution. So basically, in modular mathematics, this means that we only have one solution. Now, what we can do is to prove this theorem. And we're going to follow different steps. The first step is, in fact, a constructive proof, where we are going to construct the solution. And in step 2, we are going to prove the uniqueness. Now, the way that we are going to prove the theorem by construction is very interesting, because the proof itself will provide the solution, the steps, how to apply the Chinese remainder theory. Here we have all the elements related to the theorem. So the first step is, in fact, we define capital M, which is the product of M1, M2 up to Mn. And then we define capital M index I, which is equal to M divided by Mi. So when we look at capital M1, it's the product of M2 up to Mn. So basically the parameter equal to I is, or the modulo I is kept out of this product. Now the next thing is we claim that the greatest common divisor of the modulo index 1 and modulus, let's say large M index I is equal to 1, which means that they are in fact relatively prime integers. We suppose that D divides Mi and D divides capital Mi. When we suppose this, then we find that all Mi are relatively prime. We have that for D and J, for J is not equal to I, that we have here the result that D divides the greatest common divisor of Mi and J, which is equal to 1, because all those moduli are relatively prime. So basically this is the only possibility that we can have. The JCD is always equal to 1, D divided by the JCD. So it means that D is equal to 1. That's the only possibility. Let's have a look at the next step. So we already have capital M is the product of all the moduli. Mi, capital Mi is the modulus capital M divided by the modulus Mi. When we look at this, we already have proven that the JCD of Mi and capital Mi is equal to 1. Because the fact that we divide M by Mi, we don't have Mi there, and all those parameters means that there is not any parameter equal to Mi. So they're all relatively prime. Now, the fact that we have is that the GCD of M index I and capital M index I is equal to 1. We can say that Mi has an inverse modulo of small mi. That's one of the elements that we've already discussed before. Now, let us assume that X index I is that inverse. Then we can write that Mi times Xi is congruent with 1 modulus Mi. So that's based on what we've seen in the previous video, that when those numbers, let's say when Mi has as inverse Xi, so we can say that Mi multiplied with the inverse is congruent with 1 modulus Mi. Based on this, we can say that this is possible because we know that the GCD of small mi and capital Mi is equal to 1. Otherwise, we wouldn't be able to say that this exists. Now, the third step in constructing the solution is, first of all, we know that X index I times capital Mi is congruent with 1 modulus Mi. Now, we say that Xi multiplied with Mi is congruent with 0 modulus Mj for j not equal to I, because Mi is a multiple of Mj. Whatever Mj I use, whatever the value is, Mi is always a multiple because it's there. It's still there in the product. Now, what we can consider now is we say that X is a linear combination of Xi, Mi, and Ai. And Ai are the coefficients of the linear congruences. Mi are the moduli, and Xi are those inverses of capital Mi. Now we can say that x is congruent with that sum, modulus Mi, and all the elements where we have I not equal to j, all those elements, these are equal to 0. So basically, we find only one element which is not 0 modulus Mi, which is xi, mi, ai, and we can say that x is congruent with ai modulus mi, and I is between 1 and n, because we know that xi is equal to or is congruent with 1 modulus mi. So basically, we have completed a solution where we find that x is the sum of the inverse parameters xi multiplied with the moduli index I and a index I. The thing that we have to do now is to see, is this unique? And we have to say, to prove that it's unique, I will suppose that we have two solutions that comply with the set of, or the system of linear congruences, x and y. So basically we can say that x is congruent with ai modulus mi for I larger than or equal to 1, but smaller than or equal to n. And the same applies for y congruent ai modulus mi. So basically what we can find here, that x minus y is congruent modulus mi, which means that mi divides x minus I. And when it divides x minus y, it means that they are a multiple, and this also leads to the fact that m, large M, divides x minus I, which we can say x is congruent y modulus m, and basically it says that when we have x or when we have y, y is a multiple of x. So basically there is one unique solution. Let's have a look at the original Chinese system of linear congruences. We have the x is congruent with 2 modulus 3, x is congruent with 3 modulus 5, and x is congruent with 2 modulus 7. So basically when we look at those elements, we can define large or capital M, which in this case is 3 times 5 times 7, which is 105, and we can also calculate m index 1, which is equal to m divided by m index 1, which is equal to 105 divided by 3, which is 35. Then we have m index 2 is equal to m divided by m small m index 2, which is 105 divided by 5, which is 21. And then we have m index 3, which is equal to capital M divided by m index 3, which is equal to 105 divided by 7, it's 15. So this is the first start, the first element what we can do. And now we can write in these elements here that we have capital M1 x1 is congruent with 1 modulus 3, M2 x2 is congruent with 1 modulus 5, and capital M3 x3 is congruent with 1 modulus 7. Let's start with the capital 1. In capital M index 1, x index 1 is congruent with 1 modulus 3. So when we look at the equation, we see that M1 is equal to 35. So we can write here that 35x1 is congruent with 1 modulus 3. And this we can also write as 2x1 congruent with 1 modulus 3. Basically, we have, in fact, 3 times 11 is 33 plus 2, so the remainder is 2. So we can say that this equivalence exists. So we can have here 2x index 1 is congruent with 1 modulus 3. When I multiply both sides, I find 4x index 1 is congruent with 2 modulus 3, and the 4 and the 3 we can say finally that x index 1 is congruent with 2 modulus 3. So we find the first value of x. The same we do for capital M2x2 is congruent with 1 modulus 5. So basically I put here 21x2, capital M2 is 21, is congruent with 1 modulus 5. 21 and the modulus 5, we can replace this by x2, and we can say that x2 is congruent with 1 modulus 5. So just to remember, 21 is equal to 5 times 4 plus 1, so the remainder is 1, so we can write this equivalence. For the third and the last, we can have here 15x to the third is congruent with 1 modulus 7. So we can say that 15 is 2 times 7 plus 1. So we can replace this congruence by a simplified version of the congruence, which is x index 3 is congruent to 1 modulus 7. Based on these elements, I can write that x is that linear combination. So we have x is 2 times 35 times 2, plus 3 times 21 times 1, plus 2 times 15 times 1. And we find when we add those elements together, when we complete the calculation, we find that x is equal to 233. So basically we can say here that we have a congruence between 233, which is congruent with 23 modulus 105. So our solution is 233. We can do the same for another system of linear congruences. Now we have x is congruent with 3 modulus 7. X is congruent with 2 modulus 9, and x is congruent with 3 modulus 5. Based on this, we can define that capital M is 7 times 9 times 5, which is 315. So we can say that capital M index 1 is equal to 45. Capital M index 2 is 35. And capital M3 is equal to 63. And we can write the different congruences. So for the first one, we can say that M1x1 is congruent 1 modulus 7. So M1 is 45. 45 modulus 7 is in fact 42, which is 7 times 6 plus 3. So we can say 3x1 is 1 modulus 7. When we multiply both sides with 5, we can say 15x1 is congruent 5 modulus 7. And we can say that this can be replaced by x1 congruent 5 modulus 7. Again, 15 is 2 times 7 plus 1. So when we go for M2x2, we can say it's 35x2 congruent with 1 modulus 9. So basically we can say here 9, well, we have 4, which is 36. So we have basically 3 times is in fact 27. And we basically find x2 is congruent with 8 modulus 9. So when we do the calculation, we find this congruence. We do the same for M3x3. We have 63 x3, which gives us the same like 12 times 5 is 3 modulus 5. So we find here at the end when we do the calculation that x3 is congruent with 2 modulus 5. So you can do the calculation and you should find the same number. I did the steps a little bit faster. Now what we can do here is basically now we have all the elements for the solution, and I can say x is equal to that linear combination. So we can say that x is 3 times 45 times 5 plus 2 times 35 times 8 plus 3 times 63 times 2, which gives us a total of x is equal to 675 plus 560 plus 378 is 1613, and the final solution is 1613 is congruent 38 modulus 315. So basically we find the solution here based on the Chinese remainder theorem. Like I said, the Chinese remainder theorem is very important. We will use it in operations on large integers. So that is what I wanted to show you in this session. You know what the Chinese remainder theorem is. We have proven that it exists and that it is unique. We did some exercises how to find the solution for this system. And in the next session, we will look at computer arithmetic with large integers. We will see how we can use these congruences and the Chinese remainder theorem to do arithmetic with those large integers. That was quite a long session. Anyway, you're doing a great job, and I'm looking forward to seeing you in our next video. Thank you, and bye-bye.